The AP Chemistry exam has many graphs that represent a visual representation of data, and you'll need to understand how to use those graphs if you want to do well on the exam. In this video, I'm going to show you the 14 graphs you've got to understand before you take the AP Chem exam in May. Hi there, my name is Jeremy Krug, and this is the place for all things AP Chemistry. If you're new here, thanks for stopping by. Welcome. Make sure you check out the playlists, that's where the action is, and if you like what you see, don't forget to smash that like button and subscribe. It really does help. The best compliment you can give me is to recommend my channel to your friends and classmates. And if you're serious about getting that 5 on the AP exam, you'll want to check out my ultimate review packet for AP Chemistry. It has full unit summary videos for each of the 9 units in the course, study guides with full answer keys, multiple choice and free response practice questions, my exclusive tips and tricks, along with 2 full practice exams and complete explanations. You can get a free trial over at ultimatereviewpacket.com. It's the best review resource out there to get you ready for the big day in May. Now, here are the 14 graphs you've got to know for the AP exam. Graph number 1. Mass spectrometry diagrams for pure elements. You need to be able to take a mass spectrum diagram like this, interpret it, and determine what element it represents. This diagram has 3 peaks, so that means this element has 3 isotopes. The taller the isotope, the more abundant it is in the sample of the element. Here, the isotope with a mass number of 88 has by far the greatest abundance, and the one with a mass of 87 is the least abundant. We can take the data from the graph and estimate the element's average atomic mass and determine which element we're looking at. So to solve for the average atomic mass, we take each isotope's mass and multiply it by the decimal equivalent of its percentage abundance. The 86 isotope is 10% abundant, the 87 isotope is 7% abundant, and the 88 isotope is 83% abundant. We multiply all of these and then we add those products together. And we find that the overall weighted average for the element is 87.73 atomic mass units. When we match that up to the periodic table, we find it's very close to the value for strontium. So be able to interpret a mass spectral diagram. Graph number 2. A photoelectron spectroscopy graph. In photoelectron spectroscopy, we successively strip every electron from an atom until there are no electrons left. In these graphs, each peak represents an atomic sublevel. Since this graph has 5 peaks, the element must have 5 sublevels. We represent those sublevels in order. The peak on the far left will always represent the 1s sublevel. And if you've written electron configurations, you know that in order, it then goes 2s, 2p, 3s, and 3p. The height of each peak represents the relative number of electrons found in that sublevel. If you've written electron configurations, you know that every s sublevel holds a maximum of 2 electrons. So each of these s sublevels has 2 electrons each. The 2p peak is 3 times higher than the s peak, so it must have 3 times as many electrons. So that would be 2p6. And notice that the 3p peak is twice as high as the s peaks, so it must have twice as many electrons. That makes it 3p4. We see that this electron configuration corresponds to the element sulfur. Now the x-axis shows us that the binding energy gets lower as you move toward the right. This shows us that these outermost electrons like 3s and 3p, which we call valence electrons, are the easiest to remove since they're bound to the atom with the least energy. That makes sense because the outermost electrons in an atom have the greatest amount of energy, so it requires less energy to remove them. Graph number 3. Potential energy between 2 atoms. This graph represents the potential energy between 2 atoms as the distance between those atoms changes. When a chemical bond forms, it's always at the distance where the potential energy is the lowest. So that's why you always want to focus on the bottom of that curve. So if the question asks us to determine the bond length between the atoms represented by this graph, we can say the bond length will be 200 picometers. If we're asked to determine the bond energy, we look at the y-axis and that same lowest point on the curve. The bond energy will be about 250 kilojoules per mole. The value is negative here on the y-axis of the graph, but that's because forming a bond always releases energy, which is why it's negative. However, bond energy is the energy it takes to break the bond, which is why bond energy will always be a positive number. Graph number 4, relationships among properties of gases. Different properties of gases have different relationships between them. For example, the pressure and volume of a gas are inversely proportional to each other. The pressure goes up when the volume goes down. And likewise, the pressure goes down when the volume goes up. So the graphical relationship between pressure and volume looks like this. With most of the other relationships, you'll see a more linear relationship. In the second graph, volume and temperature are directly proportional to each other. So the graphical relationship is linear with a positive slope. In the third graph, it's also linear. When temperature goes up, pressure goes up. And in the fourth graph, it's the same thing. When temperature and pressure are held constant, the volume increases as the number of moles increases. So be familiar with these graphs. Graph number 5. The Maxwell-Boltzmann distribution curve. The Maxwell-Boltzmann distribution curve looks like this, and the idea behind it is that for a sample of matter, at higher temperatures, more molecules have a higher velocity. Notice that at every temperature, some molecules are moving slowly, but at higher temperatures, like 500 and 1000 kelvins, a greater proportion of molecules are moving faster. And this explains why chemical reactions have a higher rate at higher temperatures. As an example, let's say that the minimum velocity required for a successful collision in a certain reaction is 750 meters per second. You'll notice that none of the molecules at 100 kelvins will react, because none of those molecules have a velocity of 750 meters per second. At 200 kelvins, a very small fraction of the molecules will react. At 500 kelvins, we see even more molecules colliding with that velocity. And at 1000 kelvins, most of the molecules will get past the mark. So at higher temperatures, chemical reactions take place more quickly. Graph number 6, a best fit line for spectrophotometry. Spectrophotometry is a method of analyzing the concentration of an unknown solution. And we do this by making solutions with a known concentration, and we plot their absorbances on a graph like this. We draw a best fit line, and then we determine the absorbance of the unknown and match it up to the curve. So if this is our best fit line, and the absorbance of an unknown is 0.33, well, we can match that point up to the x-axis and see that the concentration of nickel ions in the unknown solution is 0.32 molar. It's relatively straightforward, but you do need to know how to read the graph. We basically just have to match up the absorbance on the y-axis to the concentration on the x-axis. Graph number 7, graphical determination of reaction order in kinetics. A straightforward method of determining the order of a reaction with respect to a reactant is to make 3 different graphs, like we see here. We can plot the concentration of a reactant versus time, like we see in the first graph. Then we can plot the natural log of the concentration of a reactant versus time, like we see in this bottom graph. Then we can plot the reciprocal of the concentration versus time, like we see in this other graph. You'll find that only one of these graphs will make a straight line, and the straight line graph is the one that tells you the order. If this first graph had been a straight line, the graph of concentration versus time, then the reaction would have been 0 order. If this graph on the bottom is a straight line, the graph of natural log of concentration versus time, which it is, then the reaction is first order. If this other graph on the top right had been a straight line, the graph of reciprocal of concentration versus time, then the reaction would be second order. Once again, you just have to find the graph that's a straight line, and that tells you what order the reaction is. Graph number 8, reaction energy profile. For every reaction, we can draw an energy profile that plots how the energy of the molecules in a reaction change as the reaction progresses. On the AP exam, you'll have to identify different parts of that reaction energy profile. For example, the energy of reactants will always be the distance from the bottom of the graph up to the beginning. The energy of products will always be plotted from the very bottom to the ending point right here. This peak represents the energy of the transition state, or activated complex. It's the energy plotted from the bottom of the graph to the very peak of the top of the curve. The activation energy of a reaction, often abbreviated E sub A, is the distance from the beginning of the curve up to the peak. You might notice that the energy of the reactants plus the activation energy is equal to the energy of the transition state. The change in enthalpy, which we abbreviate delta H, is the difference between the starting point of the graph and the ending point of the graph. Since this reaction has a net loss of energy, we can say that the delta H is a negative number and that the reaction is exothermic. If it were the opposite, where the reaction had a net gain of energy, delta H would be positive and the reaction would be endothermic. If a catalyst is added to the reaction, this is how the profile would change. Adding a catalyst causes the activation energy to go down and the energy of the transition state to go down. Adding a catalyst makes a reaction go faster because more molecules can attain the activation energy. Notice that adding a catalyst does not change the value of delta H, and it doesn't change the energy of the reactants or products. Graph number 9. The multi-step reaction energy profile. This other type of energy profile is similar to the one we just saw, except here the number of peaks corresponds to the number of steps the reaction's mechanism has. Since this profile has 3 peaks, the reaction must have 3 steps. Each peak, or step, in the reaction has its own activation energy. Notice that the third step has the highest activation energy, so the third step would also be the slowest step in the mechanism. We also see that the second step seems to have the lowest activation energy, so the second step would be the fastest step in the mechanism. Graph number 10, the heating curve. A heating curve is just a graph that shows how the temperature of a substance changes as heat is added. If you take a solid and you start adding heat, the temperature goes up. But when it reaches the melting point, the temperature stops changing. It stays constant during the melting process. Once the substance is completely melted and heat continues to be added, the temperature starts rising again, and it keeps going up until it hits the boiling point. When it reaches the boiling point and heat continues to be added, the substance boils, but the temperature stays constant. Finally, when all the liquid has boiled away and become a gas and more heat is added, the temperature of that gas keeps going up. Be familiar with all the regions of this heating curve and which state of matter exists at which parts of the graph. Notice that the energy it takes to melt a certain amount of a solid at the melting point is called the heat of fusion. The amount of energy it takes to boil a certain amount of liquid at the boiling point is called the heat of vaporization. Graph number 11, the cooling curve. We can take the heating curve we just saw and make it go backwards, except it's no longer called a heating curve, it's called a cooling curve. It's the same concept, except we're removing heat. We can cool a gas until it gets to the condensation point, and while the gas is condensing, the temperature stays constant. Once it's become all liquid, heat is removed and the temperature starts dropping again. When that liquid reaches its freezing point, the temperature stays constant while it's freezing. And then, as you remove heat from a solid, the temperature continues to drop. The two graphs are essentially the same. They're just going in opposite directions. Graph number 12, a graph of concentrations as substances approach equilibrium. Chemical equilibrium is a state achieved when the concentrations of all substances in a reaction stay constant. At equilibrium, a reversible reaction has not actually stopped. It's just that the rate of the forward reaction equals the rate of the reverse reaction. On this graph plotting the concentrations of reactants and products in a reaction, we can say that this point is where equilibrium is established, because after that point, all substances in the reaction maintain a constant concentration. Graph number 13, the titration curve. Studying acids and bases, we discuss how different substances are more or less abundant over the course of a titration. A titration curve, like this one here, is basically a plot of the pH of the solution as titrant, in this case sodium hydroxide, is added. There are some key parts of a titration curve you need to know about. This inflection point represents the equivalence point of the titration. This is the point where the number of moles of acid is equal to the number of moles of base that have been placed into the titration flask. We can look at that equivalence point and decide what type of titration we're looking at. Since the equivalence point for this titration has a pH greater than 7, we know that it's a strong base, weak acid titration. If the equivalence point had been less than pH 7, it would have been a strong acid, weak base titration. And if the equivalence point had been exactly pH 7, then it would have been a strong base, strong acid titration. An important point on a titration curve when a weak acid is involved is the half equivalence point. In this titration, it takes 25 milliliters to reach the equivalence point. So half of that would be 12.5 milliliters. At the half equivalence point of a titration, the pH is equal to the pKa of the acid used in the titration. So in this curve, that seems to be right around 4.8. So the pKa of the acid is 4.8. So the Ka of the acid would be about 10 raised to the negative 4.8 power, which you could easily calculate. It's important that we see how different substances become more or less plentiful as the titration progresses. If the pH is less than what you have at the half equivalence point, the weak acid is going to be more plentiful than the conjugate base. However, once you've gotten to a point in the titration where the pH is higher than it was at the half equivalence point, there's more conjugate base in the titration flask than there is weak acid. Now, that means that at the exact halfway point, right here at 12.5 milliliters, the weak acid has exactly the same concentration as the conjugate base. What about the equivalence point itself? Well, at that point, all of the weak acid is gone. It's all been reacted. The conjugate base is the only important species here that's still present in the flask. Once the titration continues past the equivalence point, the reaction mixture has excess hydroxide that's being added, which explains why the pH keeps shooting up so fast. So past the equivalence point, the hydroxide ion is in excess. Graph number 14. Titration curves with polyprotic acids. When you see a titration curve with more than one inflection point, that means the titration has more than one equivalence point. Since this curve has two equivalence points, it must be a diprotic acid. Over the course of the titration, two hydrogen atoms dissociate, one after the other. Since it has two equivalence points, it must also have two half equivalence points. The first half equivalence point would be halfway to the first inflection point, right around 5 milliliters. So the first pKa of the acid is about 2.1. Halfway between the first equivalence point and the second one is where we'd find the second half equivalence point, right around 15 milliliters. Since the pH at that point is about 6.5, the second pKa for the acid must be about 6.5. So those are the 14 graphs you've got to know for the AP Chemistry exam. Hey, I hope you learned something from this video. If you did, please slam that like button and leave a comment down below. I really appreciate it, and it really does help out the channel. Thanks for watching. I'll see you soon.